Today I'm going to be talking about a software package I've been working on called PyTeCK, which is a package based in Python, obviously we're SciPy, for automatically testing chemical kinetic models. And right now I'll just point out all my kind of contact info, Twitter, GitHub, webpage, email. It's all kind of variations on my name, so I'm not too hard to find. So first off, PyTeCK, it's a fairly unimaginative acronym that stands for Python-based testing of chemical kinetic models. Unfortunately, just because I haven't had time and I'm also not particularly visually creative, I don't have a nice, neat logo for it yet. Hopefully that'll come later on. So before I get into exactly what PyTeCK does, I want to spend a little time motivating the big picture. Chemical kinetics is related to combustion, so reacting flows provides energy. But a lot of people might still ask, and they do ask me all the time, why do we still study combustion? Isn't this old, dead technology? It's been around since cavemen. Combustion's on the out. We're trying to replace all of our fossil fuel-based technology with newer, cleaner things, and we are, and we should. Unfortunately, combustion still provides about 85% of the world's power, and that's not going to go away anytime quickly, easily, unless we have, I guess, depending on how the election goes, things could change pretty quickly. But yeah, so it still provides a lot and the majority of our power, and it's really vital, and I and many people who work in combustion agree that it's vital that we develop alternative renewable sources of energy. But just because it's still providing so much, combustion is going to remain the dominant source for the next few decades at least. And so in the meantime, we can try to do better. And so that means developing new, more efficient engine technology. It also means trying to develop more renewable fuels, biofuels, things like that. So we have areas of improvement. We can try to reduce the impact of the technology while we're trying to further develop alternatives. So with that in mind, what can we do in terms of combustion technology? Well, first thing you can do is try to improve efficiency. That means getting more bang for your buck. You drive your car a certain distance. Can you do it on less fuel? And there are current federal mandates to try to improve consumer fleet efficiency from an average of 30 miles per gallon up to 54.5 miles per gallon by 2025. That's a pretty optimistic milestone. I'm not sure how that's going to happen, but that's our goal. We can also try to make our technology cleaner. So that means reducing emissions of things like carbon dioxide, nitrogen oxides, and soot, which are bad for air quality and things like that. So, combustion technology exists to take fuel and turn it into carbon dioxide and water when it burns in the air. So we can't eliminate the carbon emissions completely, but we can try to do better, and we can try to reduce those other bad emissions. So these days, computational modeling of combustion really drives design. It used to be this Edisonian prototype and build and test paradigm. Things are really driven by modeling these days, and that means that we have to have good and accurate models in order to actually predict how something's going to perform before we go and test it. Otherwise, what's the point of doing the model if it's not accurate? So I want to take just one second to explain a little bit about what's going on when we model combustion and a reacting flow. So here's a simulation of a flame. I did not make this simulation. I think this came from Sandia National Lab. They had a nice, pretty picture. So what's going on in this flame? So you have fuel. It could be something like gasoline, hydrogen, natural gas. It's reacting with the oxygen in the air, decomposing into smaller chemical species. It's releasing energy. That energy release is raising the temperature of the gaseous mixture. This causes the density to vary. It causes the pressure to increase. Now, in order to model this, you have to solve what's known as the Navier-Stokes equations, which are some fairly complicated equations that essentially stem from Newton's second law. And they govern the motion of the fluid and basically capture the transport of the fluid inside this flame. And that can include contributions from the chemical reactions that are occurring, things like turbulent mixing, radiation emissions, all sorts of different physics. So solving this is a very multi-physics problem. Right now I'm focused just on the chemistry part of that, just the models for the chemical reactions that are occurring in this. We have a pretty good feel for the fluid side. Like the Navier-Stokes are very well understood. That part is not, well, very well understood is maybe not very easy to solve, but at least we're pretty comfortable with the equations themselves. But the chemistry, we have to have models for. And what those models look like, I want to spend just one slide on. So for hydrogen oxidation, now if you've learned anything from a basic chemistry class, you learn about reactions between multiple species. You might learn about, okay, you've got hydrogen and it's burning in air, and that turns into water. If you've got a hydrocarbon, you'd also get carbon dioxide out of this, right? So this is what you learn as the overall reaction. This is what's going on. Well, for correctness, we should have things be properly balanced. This is the overall oxidation reaction, but this isn't actually what's happening when you take hydrogen, combine it with oxygen, and turn it into water. Those things do not necessarily directly interact very often. Instead, this is what's happening. The previous thing was what you start with and what you get at the end. This is how it gets there. And so in reality, you have all these smaller intermediate species, all these elementary reactions that are occurring and when you take hydrogen and oxygen and combine them to try to form water. And this is releasing energy. It's releasing all these intermediate species. And so it's fairly complicated. And in order to get accurate predictions in our simulations of combustion, we need to use these fairly detailed models for the chemistry, and they need to be accurate in order to get the right answers. Now, every single one of these species has information about its thermodynamics and what's its specific heat, entropy, enthalpy, things like that. All the reactions have multiple properties in order to characterize their rates. At minimum, there's at least 3 parameters per reaction. Often there's more because there's things like pressure dependence. So they get very complicated, and there's a lot of numbers that need to go into modeling this reaction system. And even for something like hydrogen, which is a very basic fuel, we do not have an agreed upon model. And as I'll show you later, there are dozens of models for just this. Some people will say, well, this reaction is less important than this one. Some of these numbers are different. We've done some experiments. We've done some simulations. There is no accepted model for hydrogen, and that's our simplest fuel. And so we have a lot of models for all the fuels that we want to try to simulate, but no accepted model for how they behave, even though we've been studying these things for hundreds of years, right? So anyways, let's say we have a model for hydrogen, something that looks like this. Well, if we want to use it, we probably want to check and make sure it works okay before we put it into some simulation of an engine. Otherwise, why waste the time? So, you might think, well, can't you just go do a simulation of whatever engine experiment you're about to do with this model and then somehow validate that? Well, that's really hard to do because kind of experiments of more realistic applications are way too complicated, and they're very hard to characterize, like what are the boundary conditions, what's really going on. If there's a difference between my prediction and my experiment, is it due to the chemistry model or is it due to all the other stuff that's happening, right? So when we try to do validation of these models, we actually use very, very fundamental idealized experiments where we've tried to eliminate all the uncertainties and focus just on the chemistry. So there's a couple of different experiments that we do. I do not do these. You'll hear from Brian Weber in a few talks who does some of these experiments. I just do modeling. But one of the basic ones is a shock tube, which is basically a long tube, and you get a shock wave that propagates down. It causes temperature and pressure to raise really quickly, and then you wait and see how long it takes for the mixture to ignite. A rapid compression machine is like a very, very controlled engine cylinder where you have a mixture of your fuel and oxidizer, and then the piston really quickly smashes it together, raises the pressure and temperature. You wait and see how long it takes to ignite. You can have something like a counterflow flame. So you can actually see flat flames there. You've got 2 streams of gas mixtures blowing at each other, and it causes a flat flame in the middle. You can use that to measure things like the velocity of the flame. And then another one is a jet-stirred reactor. This is where you have a specific residence time. The mixture gets in there, and it has a certain amount of time to react before it exits. And that's all these things. The point of all these things is that they're fairly easy to model without introducing any assumptions other than the chemistry itself. And so when we check there's an asterisk there. There's always going to be some things that we can't capture, but we at least try to model these in a very idealized ways. So most of these are not multidimensional. They're either just time-based or maybe one dimension. So that really allows us to simplify things quite a bit. I'm not going to talk at all, and in fact, PyTeCK doesn't support anything related to those bottom 2. It's really just focusing on these ignition, kind of simple ignition experiments. So what is autoignition? Well, autoignition, this is a plot of temperature as a function of time. Essentially, you have your mixture of a fuel, oxidizer, so oxygen, maybe with nitrogen in it, and you have it sitting there at some temperature and pressure and mixture composition, and you wait. And after a certain amount of time, it ignites. That dot right there is the ignition delay time, and that's something that we measure experimentally and then compare against model predictions. And so we want to try to capture that ignition delay time accurately. It's relevant to things like what's going on in internal combustion engines. It's a way for us to check and see how well our models are doing. All right, so that seems great. So here's one of the problems. Experimental data that comes out of these idealized experiments that we've been doing for decades. So one way that this experimental data is distributed in the literature, and this is kind of a historically has been done, still is being done by some people, is you put it in a table in the PDF, right? And then it just gives you, oh, here's the output, here's my initial temperature, here's the ignition delay, maybe the pressure, some other things. All right, that's not so great because then I have to try to manually encode this and grab it from the PDF. There's some tools that allow you to do that, but it's really, it's not very helpful. It's certainly not machine readable. In some cases, people just give you a figure, and you're expected to, if you want to use this, go and use some tool to try to scrape the data points off that figure. These days, people are getting a little bit better about sharing, say, like an Excel spreadsheet or a CSV file that has some information about that experiment. For example, in this case, this is one that I even kind of hacked together based on data that they provided in a 2001 paper where it's the temperature, pressure, and then the ignition delay. Nothing else, no other metadata about the experiment, other than what you add to it yourself. And then in the worst case, an email plea. Hello, I read your paper. Can you please send me your data? In this case, Jeff from McGill was responsive and sent it to me, but others were not so helpful, or their emails are changed. In one case, or multiple cases, somebody had died because the paper was too old, and that data is lost forever, right? So that's one problem, is that we want people who develop these models aren't going to have access to the data unless they did the experiment themselves. And if that's the case, they're only checking it against their experimental data and not the wealth of data that exists in the literature. That's a problem. The other problem is that people frequently do qualitative versus quantitative comparisons of predictions. So in this case, this is you can see the points, if you can see them, are experimental results, and the lines are the predictions, and this is a log plot on the y-axis. And so I don't think that this, you can't see that. I don't think that those data points are agreeing very well. This is how they described it in the paper. The calculations show good agreements with experiments. And then a sentence later, except for at temperatures less than 1,000. And if you can't see, that's everything to the right of this point, which is more than half the data. It's like, oh, but it agrees well. Okay, I don't really think so. Similar paper, again, a log plot, a log scale on the y-axis. In general, the model well predicts the reactivity. We're talking multiple factors of difference. And maybe that's acceptable, but we probably shouldn't use these hedge words that are very qualitative and mean nothing. Good, reasonably well, that doesn't mean anything. It doesn't help us. So what I'm proposing is a solution, and I'm not necessarily novel in proposing this, or solutions, I should say. One is, and this isn't in the title, a new standard data format that I'm going to try to make people use, or ask people to use, or take their data and convert it into this format, and then say, here, now you can use it. That I'm calling ChemKED, which stands for just Chemical Kinetics Experimental Data Format. Pretty unimaginative. So that combined with now PyTeCK, which is this new software package that I'm going to talk to you a little bit more about. So really quickly, I want to talk about ChemKED because I really like it. It's written in YAML. So it's both human and machine readable. This is an example of one ChemKED file that I'll talk about some of the elements more in a second. So one of the benefits of using YAML, as opposed to some other people in the past have tried to propose using something like XML, which is not very fun to try to write yourself or edit or read. YAML's very readable, both by humans and machines, and parsers exist for pretty much everything. You can find parsers in libraries in whatever language you're trying to use, particularly Python. It's pretty easy to interact with. So the components of these ChemKED files are some metadata about the file. So in this case, the file author, my ORCID, something about the reference. And so I've included like the DOI, authors, a list of authors in terms of their name, ORCID if available. In this case, none of them were. Journal, things like that. Then some detail about where this data came from. And then some also data about the metadata about the experiment. Like this is an ignition delay experiment done using a shock tube. I'd like to put in more about where this came from, institution, things like that, if available. Then there are some common properties which can be shared across multiple data points. So frequently you'll keep the composition the same, so the same amount of the fuel, and then change something like the temperature. So if there's any common properties, you can add that. This is just a convenience factor using anchors and tags in YAML. You don't have to use this. It just is helpful for reducing the amount of information you have to type. Then things like how are you detecting ignition, which I'll talk about more in a sec. And then the data points. It's just an array of these data points with the temperature given with units and the value, pressure, composition, and then the actual ignition delay. So this contains all the information you would need to try to reproduce this experiment computationally, compared to a figure that you get in a paper or a CSV file. The goal of this is to give you everything that you need in order to reproduce it. So that's ChemKED. So PyTeCK, which I'll before I get into what it's doing, I just want to say that it's using quite a bit of the kind of common scientific Python elements that are out there. So of course I'm using version control with Git and GitHub. It's all, I'm doing this openly. It's a public repository, so you're welcome to check it out. Of course I'm using NumPy for manipulating arrays and data. I'm not using too much of SciPy other than some spline interpolation, which if I have time, I'll talk about where I'm using that. Pint for interpreting and converting units, which I'll talk in the next slide, is a godsend. HDF5 for saving the results of these simulations. That's done using PyTables. All the chemical kinetics work is done using Cantera, which I'll come back to in a sec. This is not something that I think a lot of people in the room are going to be familiar with, except for Brian Weber, who's also in my field. Pretty much everybody else probably hasn't heard of it. I'll talk about it more in a sec. It's doing the main heavy lifting in terms of the chemistry. Unit testing using PyTest, and then I am doing continuous integration on Travis. So I want to talk about PyTeCK for one sec, or Pint for one sec. So this is there to interpret all the units given in these ChemKED files. So for things like pressure, frequently people don't use just one unit for pressure. We switch between bar, atmospheres, torrs, pascals, kilopascals, and it's really nice to have something that can just read that and convert it into whatever internally I'm going to use. And so it's also, in addition to interpreting that, it's also checking to make sure that the quantities are valid. This I stole from Katie Huff and her PERC software. And so any time that it's reading a value that's given in these ChemKED files, is making sure, oh, if this is a temperature, it has to be above 0, right? And given in units that are compatible with Kelvin. If it's a pressure, it's probably got to be bigger than 0 too. We can't do this in a vacuum. And given in appropriate units. So things like that. And yeah, so thanks, Katie, for pointing me to that. Okay, so in terms of the actual components of PyTeCK, it's not a particularly complicated package because it is relying on so much else to do a lot of the work. There are 3 main modules. First one is parse files. So this one I'm not going to spend much more time talking about. It just reads all the necessary data from the YAML file using PyYAML. It also creates a list of objects that are there to represent each simulation that you're going to do to try to recreate an experiment. Said simulation objects are contained in a simulation module, which is basically there to provide a simulation class and all the necessary functions and affiliated classes, which I'll talk more about in a sec, volume profile, pressure rise profile. And then eval model, which basically runs the show. It uses those other modules, and then it uses the multi-processing module to try to do these necessary simulations in parallel rather than doing them serially, so that helps a lot. There's some other ancillary modules, such as detecting peaks to get the ignition delay I'll talk about in a sec, some exceptions, utilities, which contains the unit registry from Pint, and then the validation module, which checks if those quantities are correct. Okay, so as far as an actual simulation, these are the equations, and I try not to show too many equations in my talks. This is it. These are the equations that we need in order to simulate ignition in either a shock tube or a rapid compression machine. So we're basically looking at the energy equation for how the temperature changes, and that's coupled to conservation of mass equations, which tell us how the species change. And so we have all these equations that are coupled. Depending on how many species are in our model, we have that number of equations plus 1 for temperature. I do not need to try to solve these myself because that's what Cantera provides. Cantera uses a standard model format. It's an open source package. It's written primarily in C++, but it provides a really useful Python interface, which I think that's the way most people interact with it these days. But it does all the work of, if you have a mixture at a certain temperature, pressure, composition, what's the reaction rates? Things like that. So it does all that work for you. In this case, I mainly use it by connecting an ideal gas reactor, which is what keeps track of the properties of a particular mixture of an ideal gas. That is separated from a reservoir, which we don't really use, with a wall, and then that's kept in a reactor network, which is done to actually integrate these equations. That's all done internally in Cantera, though. I don't have to do any of that. I'm not going to talk about this because we don't have time. One thing that we do is process the results after performing a simulation. This is done, I have a time history in HDF5 file. I need the ignition delay time, so I have this time history. How do I get when it ignites? I use a detect peaks module, which basically, well, I have a figure that hasn't popped up. Let me get to that. Yeah, so if I have a time history, the detect peaks either looks at a maximum quantity or the maximum derivative, depending on how experimentally ignition was determined. Typically, it's the maximum derivative of pressure, and that's what it was done in this case for this data point here. But we can also look at temperature, and then particular species fractions, which is done sometimes experimentally. So once I have all these ignition delays, then the module that actually evaluates each model essentially goes like this. I read the experiment. I create a number of simulation objects, one for each data point. I estimate a standard deviation of experimental data, which I'll talk about in just one sec. I use a multi-processing pool, which uses workers that set up a case, then run the case. That's all in parallel. And then once they're all done and I've processed them, I calculate the error function. So the error function, another equation, I apologize, looks like this. We essentially look at the log difference between the experimental data point and the simulated data point. And then there's some contribution due to experimental uncertainty to try to weight things that are very uncertain in the bottom there. This is a number that we try to apply to a model to say how well it predicts a certain data set. The lower it is, the closer to 0, the better the agreement is. Then for a particular model, looking over all the data sets we've considered, that's a number that we can apply, an error function to this model saying this is how well it does to reproduce the experimental data that we've considered. Again, closer to 0 is better. Now, one detail there about the uncertainty, that's sigma, which is used as a weighting factor. So that represents the standard deviation of a particular data set. So this is one particular data set where you have a number of related experiments that were done while varying the temperature, and then the ignition delay is on the y-axis. So the dots are the experimental data points. You can see that you would expect, in reality, for things to change pretty smoothly with temperature if there was a perfect experiment. No experiment's perfect. There's always some uncertainty, so there's always going to be some scatter in the experimental data due to a number of sources. So one thing we want to do is try to incorporate that scatter, that uncertainty, into our model validation. And so the way that I do that here is by taking a spline fit using SciPy to this experimental data as a function of whatever independent variable, in this case it's temperature, and then I look at the standard deviation of the difference between that spline fit and the experimental data. The standard deviation of that difference is then an approximation of the scatter or the uncertainty in that. In some cases, if you have just a small number of points, you can get pretty low. We're saying it's unrealistic to have anything less than a 10% uncertainty, a 10% scatter, or variance. And the reason that we have to do this is that in combustion, most experimental papers don't report uncertainty. You do not see error bars in a lot of combustion, which is crazy because we like to think a lot of us like to think of ourselves like physicists, but there are no error bars. I think that if you tried to show that to a scientist in a lot of fields, they would be like, "What are you doing?" So we don't estimate this a lot, so we have to try to estimate it because I have to try to estimate it because the people who did the experiments don't report it or try to calculate it. All right, so that's the main components of PyTeCK. So with the time I have left, I want to do a quick example. I went and collected hydrogen, so the model that I showed you at the beginning, experimental data from shock tubes from the literature. I made this available on Figshare, the whole set. So if you look at the paper, you can actually reproduce the figure I'm about to show you. This comes from 14 different publications, 54 data sets across those 14 publications, a total of 786 data points. These publications range from 1958 to 2013. I also collected 12 models. So like I said, we don't have a standard model for hydrogen. I collected 12 from the literature. That set is also available on Figshare. These have been published from 1999 up until just last year. The reason I use this as an example is because it's a subset of the study somebody else did using a much different approach to trying to do this model, much more manual. This is PyTeCK does it all automated. So within a few 10, 20 minutes, I could basically generate this figure, which is the error function of each model with the lines indicating the standard deviation. So the error function is the average across all the data sets. The standard deviation is including the actual error function of the data set. So you can see, if you go from left to right on the x-axis, it's publication year. So just looking at the bars, you can see things are tending to get lower as we get closer to the present, which is good. That indicates the models are getting better. The deviation is also getting better. So you have less outlying bad predictions. But it's still not perfect. And even though it's 2015, we still have an error function that's 20 to 30. It should be near 0. So with that, I'm just going to wrap up with plans for PyTeCK. Right now, there's no documentation other than a README and a quick how to run it. I plan on writing a Sphinx-based documentation, hosted again, read the docs. Better functional testing. I have a lot of testing, but one area that there's a weakness is the rapid compression machine simulations. That's why I didn't show you an example that has rapid compression machine simulations. And long term, I hope to support other fundamental experimental methods like laminar flames, jet stirred reactors, because those are used also commonly to validate models. Once we get to a more stable version, I'll submit it to PyPy. So with that, I'll thank you, take any questions, and show you two different things you can visit. One is Corvallis, where Oregon State's located, and the other is the GitHub repository page. And then I'd like to thank Brian Weber, who helped with an early review, and then the reviewers from the SciPy Proceedings paper. Thank you very much.
Now we can take questions.
So, are you talking about that set of reactions or some abstraction assumption, or are you talking about parameter values?
So we're comparing the ignition delay. So experimentally, what's being measured is that time. It's a time. How long does it take from the beginning of this experiment to when it actually ignites, when it takes off? And so that's something they collect experimentally, and that's what I'm comparing the prediction of that time versus the experimental measurement of that time in this case.
Right, so my question is, what you define a model as a prediction, and how is the model defined? You're trying to validate different models, right?
Yeah, so the models come from the literature. All sorts of people come up with these models, which are the species that are involved, the chemical reactions, so hydrogen, H, radical, OH, things like that. So other people have come up with these models, which came from different rules. People are now using quantum chemistry simulations to try to estimate some of these reaction parameters, things like that. Yeah.
So say you had experimental data coming directly from the device. How would you incorporate that into this workflow? And would you force that to go through,
So not necessarily, and I think, what I don't necessarily think that I would have experimental data that's flowing directly to this. I would expect, because people when they're generating, they're doing the experiments, and Brian actually will in a little bit, we'll talk about their workflow for rapid compression machine experiments. There's some, filtering of the data. They have to do quite a bit of analysis on it. And then I expect, well, my hope is that they will provide, when they publish, here is the data set of the relevant experimental data associated with, and then all the metadata you need to reproduce that based on what we've done. I don't see it as like a real-time, because they have to do quite a bit of work to generate.
My impetus wasn't about real time.
Okay.
It was really about like keeping the machine precision that was originally
Oh.
measured or simulated.
That's a good
Right?
point.
And for provenance and other things like that.
So
I'm not saying that's necessarily relevant for this.
yeah, I don't know, because if you look at the data that's published, there's not very many significant digits in the ignition delay times, and where there can be is in things like for rapid compression machines, and I didn't have time, I kind of skipped over this, but they'll provide things like a volume history of the actual cylinder, and so that has quite a bit of precision to it. As far as them recording that, I mean, yeah, I guess I don't know the answer to that question. That has quite a bit of digits. There's a lot of numbers there, but that's also not necessarily direct from the machine. They usually do some calculations to provide that somehow. So yeah, so I'm not sure. Yeah. So and then yeah,
If it's not relevant.
I don't know. It's a good question. I don't know the answer.
Okay, we can take one more question.
So you're implementing models that you've got from papers into Cantera.
Sure.
Right?
Yeah.
So if you found a model that you couldn't implement in Cantera and someone had their own code for that, so you could use this for comparing the code.
So at least in combustion chemical kinetics, there are basically two standard model formats. One is an older model format called ChemKED, which has been an accepted standard since the 70s. So pretty much everybody uses that. And people are starting to use Cantera because it's now an open source. ChemKED is no longer open source. You have to buy it. And so if you want to use those models, you have to pay for software. People are now starting to switch to Cantera. But there are basically only two formats in the combustion community that are used, either this ChemKED format and then this Cantera format. And they are, for the most part, compatible. And in fact, Cantera provides a utility to convert from that older format to this newer one. But you're basically, in this field, not going to come across a model that's not given in one of those two ways.
You can find an element simulation to estimate the ignition time. You can just simulate everything in a very large simulation, right? So
You could, yeah. Yeah, you could, but that would require the model given in ChemKED or Cantera format, because that is describing the chemistry of what's occurring. Yeah, when you model the Navier-Stokes equations. for example, whether it's find it out using whatever. Yeah.
Well, let's thank Kyle again.
Thanks.